Hi, I'm Mark. This is my physics project. So I play a game called Osu, where the objective is to click the circles to the beat. And even though one of the slogans of the game is click the circles, you don't actually click them. You use a keyboard. Matter of fact, a lot of people don't even use a mouse. They use a drawing tablet. Anyways, let's keep going. So, keyboards. I use a mechanical keyboard to play the game, which is slightly different from a normal keyboard. We'll get to that later. This is a diagram of a mechanical keyboard switch, and basically what it's trying to show is that when you push down on the key, the spring goes down until it activates that little mechanical switch on the right, which registers a keystroke for your computer. So let's find out how much energy this switch gets when you push on it. Let's take the good old work equation, force times distance. Now, you're definitely thinking, how am I going to find either of those for a keyboard? So I did the little Google search, and I found for my specific mechanical switch that it takes 63.5 grams of force to hit the bottom of the switch, which is 4 millimeters from the top. Then I was like, oh boy, I can just plug in these numbers. 63.5 grams times 4 millimeters. No, I was using the wrong units. So I used my brain to convert grams to newtons and millimeters to meters, which gave me some uglier numbers, but they're the correct ones. With that, you can apply the work energy theorem, which is when you do work on something, you give it energy. To put that in words of this problem, I said, when you do 0.00249 joules of work on the switch gets 0.00249 joules of energy. Also, here's all my work on one screen, so Mr. B doesn't have to listen through this again. Now onto conservation of energy. The system for this energy bar chart will be you, your computer setup, and the Earth. On the left side, before you hit the key, there is kinetic energy because your finger is moving towards the switch. There is no elastic potential energy because the switch has not yet been compressed, so it cannot do work. After you hit it, some of that kinetic energy is converted into elastic potential energy because you compressed the spring. There's still a good amount of kinetic energy left because you are moving/pushing with your finger more than needed to push the spring down completely. The rest of this extra kinetic energy gets channeled through your keyboard and table to the Earth. And that brings us to part 2. Impulse, momentum, and collision. Remember how I said that mechanical keyboards and normal keyboards are different? Let's talk about that. This is a membrane key. It's probably what you're used to using. Instead of having a spring, it has a rubber dome. When enough force is applied to said dome, it essentially crumples and activates the switch. This is different than a mechanical key because the switch has no travel distance between being not pressed and fully pressed. This actually makes a huge difference in how the keyboard feels. This difference can easily be shown with a force versus time, or impulse, graph. The mechanical keyboard provides a much smoother application of force, whereas the membrane keyboard has a large bump in force as you press it. Some people prefer this, some don't. Conservation of momentum and collision. Okay, so this section probably took the longest to think of. Imagine you're a weird person who wants to quote-unquote click the circles by sliding an object horizontally at a mouse button. Let's also say that this object is a pen. This would result in an inelastic collision, and its bar chart is shown here. Anyways, yeah, that's it. Thanks for watching.